My name is Sam Swain. I've been a senior tools programmer at Lionhead Studios for the last 11 years. This talk is about 50 minutes long. There are a lot of slides, but being very visual and light on text, I'll mostly talk you through them. This talk is about the technology, techniques and tools behind the landscape, foliage, ground and object cover you see in Fable Legends. I will explain our motivation, the vision we had for it, what we achieved and how, before finally summarising our findings. Fable Legends is an online 4 vs 1 combat quest game set in the world of Albion. You play as a group of traditional Fable heroes, or as the villain controlling the creatures against them. We were looking for a very rich style of environment for Legends. Our early concept art described lush surfaces with a great feeling of depth and in the distinctive Fable style. This particular piece shows off the detailed and beautiful foliage we were after. It really embodies some of the Fable style and how the foliage should be portrayed. We had a lot to achieve. We wanted the power to express a wide variety of visuals that the landscapes of Albion cover and to stand out. We require many environment styles, from grassland to forest to villages to farmland, all with roads and paths deep in undergrowth, flowers, leaves and petals in abundance. The project is built with Unreal 4.6, which gives us a great starting point for creating beautiful games. It provides many features we could use to realise our vision for the environment. Landscape for ground surface structure of most of our maps, landscape materials for a varied visual appearance of ground surface, static mesh actors for larger visual elements of our levels. The surface foliage painting tools use static mesh instancing, which we can use for our own high quantity visual elements. We wanted to take the opportunity to extend and customise Unreal in some areas though. We wanted to be able to tweak more easily and not have all the changes baked in. Some things are hard work to redo. We wanted to be able to apply some changes globally. We didn't want to have to repaint foliage to modify attributes or general appearance. A lot of static runtime content, such as baked lighting, limits control over the final rendering. Having to use separate tools for material painting, mesh placement and surface sculpting isn't ideal. And foliage scalability is an issue, the cost of providing which is always multiplied by a number of levels and making it harder to deal with different platform requirements. As we intended to produce many quests over a long period of time, we needed better workflow in these areas. We set out to make these improvements with our own technology and tools. The key things we were aiming for are as follows. Integration. One of the main ways to empower artists and accelerate content creation is to bring together multiple elements into a single workflow to allow more to be done. The more work you can do with a brushstroke, the better. The more we can automate, the more the computer is a labour-saving device, illustrated here by the fact that the meshes and materials are reselected appropriately as the height field characteristics change, rather than just being moved to follow the surface or having to be repainted. We proposed that by storing some landscape layers separately and only combining them at runtime, we unlock the ability to work non-destructively. Here the landscape is modified, but the effect can be moved without losing the original sculpted shape. Mesh-based coverage is an important part of the visual appeal, and so we need to be able to make the best use of them possible. Our levels look very naked without them. As usual, we are limited in a variety of ways, typically storage and processing areas like these. We need to make the best use of the available resources. Our levels are fairly large and so broken into manageable chunks from both a gameplay and a technical perspective. A quest is divided into a number of arenas and interim holding areas to allow for streaming, with gameplay then divided into waves within them. Given this, we wanted a system that would allow us to take what would normally be thinly spread out over each whole level and concentrate it where it's needed and gives the most impact, i.e. around the player. To do this, we needed to be dynamic, and we decided to do mesh placement at runtime. This was certainly required in editor to give the authors interactive feedback, but we also saw this as advantageous to do in-game to improve rendering efficiency and platform scalability. The more dynamic your systems are, the more opportunity you have to balance them and get the best game experience. We can trade speed for size, GPU for CPU, and offline baked content for online computed content as best befits the platform. And with these targets platform specs, there are decisions to be made about where we want to and where we can provide these balance points. Dynamic and non-destructive tools and systems where we avoid baking steps and rigid forms of content, ease iteration and experimentation, encourage prototyping and enable more drastic changes to be tried. we can explore more and stagnate less. All of the rich landscapes in Legends can be built by hand using the standard tools, but not at the scale we needed. It's too inefficient, too laborious, and when that happens, time gets spent on other things and your end results suffer. By automating processes and using procedural techniques, you get the computer to handle the vast quantity of small details, allowing artists to concentrate on the big things. You shift things up a gear. A core idea here was to channel our foliage and ground cover through a single process, to wrap up a variety of separate visual elements into a single concept. We termed these themes. A theme encapsulates all the effects an artist's brush can have on the landscape, how elements are placed, what they look like, and where they are applied. Multiple elements applied together, effectively reskinning a surface. We will take a look at all that this encompasses. A theme describes several things applied to the ground, but mainly mesh instances, grass, rocks, plants, and landscape material choice. Themes can reference other themes to allow composition and reuse. They can include non-visual data that other game systems can use, such as surface material cues used by the audio engine for footstep sounds. In the future, we also plan to include actor placement, which would open up all sorts of possibilities, especially via the Unreal Blueprint system. We could then include sound sources, light sources, particle effects, and decals. Meshes provide the 3D surface coverage from a variety of source assets like grasses, rocks, flowers, and sticks. These are built and textured, usually with a single material, just like any other static mesh. Anything between 100 and 1,000 triangles, depending on how often they're likely to be used, typically with 4 levels of detail, down to about 10% triangle count. By instancing multiple mesh types together across the landscape surface, we provide a rich volumetric effect. They are placed and rendered using pretty much the same tech that the Unreal Foliage tools use, but it is applied differently. Unreal supports painting layers of what is effectively a multi-material onto the landscape. A theme can be set to drive one or more of these layers. The theme effect overrides the standard Unreal tools. Themes can reference other themes, combining their elements together. This comes into its own when multiple sub-themes are modulated differently, which we'll cover in a moment. Here we are blending between 2 sub-themes, one for short grass and one for long. Meshes are placed at points along the landscape surface, but we require more control. We started with scale, orientation and elevation, also allowing random variations around the chosen values. As the system was used, we added support for surface alignment and slope directional alignment too. Some of these controls are demonstrated here. Feedback from our artists drove these features, part artistic need, part problem solving. For example, surface alignment was needed for wider, flatter meshes which tend to stick out on steeper slopes. After starting with basic weight painting ability, it became clear that more control over the way it was used to determine mesh density was required. So again, we gradually added more parameters as artistic needs and problems arose. For example, range and boost controls for tuning meshes to brush gradients, cutting out very tiny meshes, and providing mesh type changes with density. Here, for example, the heavier you paint, the longer the grass. As the painted weight increases, larger meshes are introduced in favour of smaller ones, providing a gradual and interesting transition. To increase automation capability, we added modifiers to theme elements. These are procedural controls that modulate the painted density. We have 2 modifier types at the moment. First is for the surface derivatives, slope, direction and curvature. Slope allows placement to be restricted to a range of angles. For example, grass would appear on a fairly flat surfaces, but not steep banks where you might find roots instead. Direction allows restriction to a range of compass directions, so you could limit moss or mushrooms to north-facing surfaces. Curvature can be both positive, such as at the top of the slope, and negative at the bottom, both useful for grass overhanging at the top of an earth bank and earthstone clutter appearing at the bottom. The other modifier we have is a procedural pattern modifier, which uses a parameterized noise function to generate masks that can nicely break up the landscape by automatically mixing between theme types for you. Good for patches of assets like mushrooms or flowers that you would expect to clump together and not be spread around evenly. This system allows for more modifier types to be added easily. All this tech is not going to shine unless we provide the tools to use it effectively. We extended the editor with a dedicated theme mode tool panel with several subtools, additional editing widgets and controls in the 3D view, new asset types and extra information panels. Let's have a look at these in more detail. Painting tools are similar to the native landscape tools. Paint erase ability, size, strength and fall-off controls. The cursor is designed to be visible against any background and also show the fall-off range. To apply a theme to the landscape, you assign it to a theme brush. Then as you paint the weight down for this brush, the associated theme is applied to the landscape surface. By using brushes to indirectly reference themes, it means you can switch one theme for another easily. Brushes can be grouped together to control how painting them behaves. Painting brushes in one group will automatically erase all the others in the same group. This provides standard painting behavior and allows segregation of multiple visual themes from, say, multiple audio themes which don't overlap purpose. Any brushes not in any group can be painted completely independently, behaving as overlay or mix-in brushes and won't affect any other brush data. This is good for layering in features like flowers, mushrooms, or thicker patches of undergrowth. For example, here a grass theme is painted over with a path theme, and then some flowers mixed in. Because the path is in the art group, as its painted data is added, the grasses is removed since it's in the same group. Neither are affected by the flower data, as it is an overlay brush. A feature that takes advantage of this paletization of brushes is the visual differences our villain view imposes on the level design. For this, we added multiple swatches of brushes that could be switched at level load time to adjust the level appearance. The overhead villain view requires a more distinct look to the pathways through the level and clearer, more obvious foliage to avoid a noisy and distracting appearance. There are a number of other game-side systems linked to this role switching. As well as theme meshes, we change a material shader switch, mesh visibility flags, post-processing effects, and sometimes a different subset of levels is loaded. An advantage the Unreal Foliage system had over our landscape-based approach is that it can be painted onto surfaces of any orientation. It became clear that we still needed this ability for special cases such as mesh-based ground, overhangs, walls, and other such places. By allowing artists to define projection volumes, we are able to get the themes to be projected onto any surface from any direction. Whilst this isn't as truly freeform as Unreal's approach, it gives us a good compromise between tool complexity and requirements. As the projector actor, or the meshes it is directed at, are positioned in the editor, it uses the renderer to capture a parallel projection depth map of the surfaces within it. This effectively yields a miniature height map, much like the landscapes, and allows us to use all the same painting tools and instance placement code as the rest of the system. Since these two systems are abstracted behind a single interface, the tools behave in exactly the same way and allow you to even work continuously across surfaces. As well as all the authoring tools, we needed a number of less glamorous ones too. Often, with a complicated system, it becomes unclear whether everything is always working as it should and if problems have silently surfaced. We added ways to inspect, analyse and diagnose a variety of technical and performance issues. Some are visual and some are numerical. From an early stage, it became important to be able to see our painted data for visual inspection, so we provide overlay displays for the landscape where we can see the actual data values as colour intensity. There are multiple data layers on a landscape, including theme brush weights, height data and its derivatives, material weights, overlays, and we can also show a dynamic diagnostic layer with alignment test pattern and landscape component statistics drawn into it. To understand the quantity and variety of meshes placed on a landscape, we needed numerical data. In this case, a custom stats panel was created to show a detailed breakdown of what quantities of mesh types there are, where they are, and which themes put them there. This is immensely important for artists to be able to balance the performance of the levels. It's really easy to change the value a small amount and see the numbers go through the roof. Here we see the mesh spacing parameter for the 13,000 clover meshes in the scene. If we drop this by 25 units, it has the effect of swamping the level with 250,000 meshes and putting us way over budget. These tools allow us to monitor and diagnose these problems as they arise. We always planned the technical design to be sensible on its memory use, but we started off with a fairly blasé attitude, as the platforms we were targeting were pretty generous. Later on, as the game grew and we built a full understanding of how everything was fitting together, we needed to understand more closely how memory was being used. Our theme system memory stat panel gives us a breakdown of how all the themes, and some landscape, memory is used. Useful distinctions are made between static versus dynamic data use, in-game versus on-disk memory use, as well as in-editor use. We have automated performance data capture that runs overnight or can be run locally. This collects a variety of metrics from automatic level fly-throughs, AI run-throughs, or live QA sessions. This example shows our fly-through frame time throughout a quest and budget line, as well as a detailed breakdown of everything going on the GPU below. We have tools to process, visualize, and compare results to help spot regressions, spikes, or other problem areas. Here we see the theme instance counts during a fly-through compared between two overnight builds. A significant increase in instance counts in this middle section may need to be investigated. The toolset described gives our artists a large productivity boost, but there are a few other areas of the process that we should look at. In creating a quest for Legends, they all pass along a fairly standard pipeline. The use of our theme system is considered or involved at pretty much every step. At concept, foliage and coverage is an important part of the look and feel of the level. During whiteboxing and playtest of levels, the tools allow level design to rapidly flesh out and tweak the sorts of surfaces that the player should experience. The main art pass is where specific themes are reused or created from scratch to fit the concept more completely. New meshes and textures are created to support this. The prettying phase is where the artists can really go to town, layering in more detail and tidying up all the rough edges. By this time we have a pretty representative level and can assess it properly from a performance perspective. It is here that the level and its themes are balanced to give maximum visual richness within the performance budgets. The dynamic nature of the system is immediately valuable here, as it is simple to make changes to the theme definitions and visual ranges, which are directly applied and observable across the whole map. We weren't sure originally whether a library of theme assets that could be used across multiple levels was a sensible idea. On one hand, being able to change a grass mesh in one theme for a better model and have all the maps updates seems like a powerful feature. But it turns out that it's a huge responsibility to follow up and make sure that all the levels still look visually correct and are still within performance budgets. Consequently, we tend to keep theme assets within or associated with specific quests, copying suitable themes from existing levels as a starting point. We have been exploring non-destructive editing as a workflow feature to allow easy reworking of level composition and speeding up prototyping. This approach allows certain editing processes to be stored as the action to apply rather than the end result. Adjustments can be dynamically reapplied without having to manually fix up the effects of the process every time and without losing the underlying data. We employ this in a couple of places and plan to explore more in the future. The term smart seems to fit well with where this process is used, so splines that non-destructively affect the landscape shape are smart splines, and objects that do the same are smart objects. Themes with landscape material elements in don't just replace existing Unreal material weights. They are maintained separately and recomposed dynamically as edits are made. This allows you to paint down a theme, erase it, and have its underlying design reappear. This was supported mainly to aid the transition to theme-driven landscapes, but also to allow whiteboxing using Unreal landscape tools and then upgrade them to theme-driven by the art team. Mostly we go straight to theme-driven materials now. This dynamic composition is also applied to the height fields that describe the landscape surface. So far we have linear segments and areas as control primitives to derive landscape heights. These are great for prototyping basic level structure as they allow rapid manipulation of the landscape. Traditional sculpting can be used for more organic landscaping and then smart splines overlaid to create the play areas. This is most relevant at the whitebox and playtest stages of quest development as changes to shape, flow and structure are fast to make. Further along the pipeline, artists get the option to bake out the splines so they can hand sculpt on or around the finalized shapes. We plan to add support for proper curved splines and for them to also drive themes and height fluctuations, allowing much nicer results and making common features like streams, paths, roads and ditches really easy to place and manipulate. The same approaches can be applied to objects, allowing them to affect their surroundings. A tree with leaves around and mushrooms nestles at its base, perhaps longer grass and clutter collected around a large boulder. This would improve significantly the speed at which objects can be integrated with terrain and moving them around becomes trivial. I'll now take you through some of the technical details behind the features we've looked at so far. We'll be diving into the details of the theme system runtime and the features added to the graphics engine to support it. Themes are implemented as a type of Unreal asset, managed and referenced in the same way as any other assets in the content browser. This means themes are used by reference from theme brushes, so they can easily be reused, shared and substituted, with everything just updating across the landscape. Here the main path brush is being switched from a mud theme to a grass theme and back. Themes consist of fairly straightforward data structures, a list of elements with various properties. Any element in turn can support a number of modifiers. Currently these are all authored with the standard Unreal property editing panels. Most elements and modifiers in turn reference traditional Unreal asset types such as static meshes, landscape material, audio assets, other theme assets and pattern assets. For our mesh placement, we are effectively virtualizing geometry instances. Instances all have a fixed logical position in the level, but only exist when the player is close enough to benefit from their presence, this regeneration happening on demand. This allows us to concentrate our instance budget around the player and not to try and stretch it across the whole map. The concept is illustrated here from above. Examining various Legends quests, we found some have a theoretical maximum instance count of nearly 500,000 instances, but we can achieve the same visual appearance with a budget of 60,000 this way. Here we see the effect of spreading our 60,000 instance budget across a whole quest for a very sparse coverage. Across just the loaded arenas is better, but still patchy. And concentrated around the player we get a much richer, denser coverage. To support this placement approach, we manage the instances with a grid of tracking blocks. Each block calculates whether meshes are needed according to player location, triggers placement calculation, spawning of instances, and then clean up and removal as the player moves away. To give the necessary control over which areas are populated, instances are batched up using the Unreal Instance Static Mesh component. To make efficient use of these by avoiding draw calls for only a few instances at a time, for farther away, i.e. less dense foliage, is managed in larger blocks than nearer, high-density foliage. This attempts to keep the instance per component ratio fairly balanced and independent of component size. A shallow quad tree of tracking blocks is used to do this, the deeper, smaller blocks handling the closer, denser foliage. The ranges to which each level or tier of blocks are visible are set per map, as requirements vary with differing play space styles. Some examples are visualized here. The tracking system supports multiple detail nuclei, points around which the foliage density is concentrated. Normally just the player has one of these, but there are other use cases such as preloading, to ensure foliage is ready at the start of a game or cinematic, prior to teleportation, such as player catch-up or as required by gameplay mechanics, and spectator mode, when switching to different player points of view. Placement of foliage is deterministic and performed by each block based on all the placement parameters, surface data, and with a block seed to vary the outcome across the map. It's worth mentioning that for these placement calculations, the theme system maintains its own height and derivative buffers as 2D float arrays, and theme, material and mask data as 2D byte arrays. These are the same resolution as the landscape, about 30 units, and are only compressed when packaged up onto disk. The original plan specifies a powerful distance field-based approach to be applied in layers for different scales of object. Due to its complexity, unproven efficiency, and unclear requirements at the early stages of the project, we decided to start with a simpler temporary placement algorithm instead. This just placed meshes based on a simple honeycomb pattern, with some random offsetting applied to the positions to break up the regularity. This is proving a surprisingly effective solution. We may revisit distance field and packing-based approaches later. We can get away with this simple approach because assets designed for ground cover are mostly round. With a bit of overlap, circle packing provides fairly even coverage and volume filling effect. This intersection can be increased, spacing decreased, to thicken up the foliage, and doesn't really create intersection problems as foliage tends to be sparse and thin in nature, the increased overlap mimicking the intertwining that happens naturally. The advantages of this simpler approach are a guaranteed maximum density and minimum spacing, avoiding any dependency on the placements within neighbouring blocks. It's simpler to implement and faster to calculate. In anticipation of a fairly intense placement calculation algorithm, the system was designed to offload mesh position calculation jobs onto background worker threads. The duration of each placement job is difficult to predict, and the work likely to be hard or inefficient to time slice, so running them in an environment that wasn't constrained to some portion of the frame period made life easier. The more advanced placement algorithms rely on large amounts of working buffer, which is tricky to marry up with the available job scheduling systems, so we have dedicated theme processors running on low priority threads, 1 in the game and 4 on the editor. The actual placement and removal of mesh instances requires interaction with the Unreal game systems and has to happen on the main game thread. Profiling showed issues when trying to spawn too much content in each frame, so this is performed progressively based on time spent or quantity placed each frame. We limit to half a millisecond placement time, but this isn't a problem as placement isn't normally needed at a high rate. Worst case is if the camera or player jumps to a new area, but as long as this can be preempted, then we can spin up the foliage in advance. There is some scope to boost placement rates briefly if needed. Normally, whilst editing landscape in Unreal, the tools talk to the engine to read and write the material and height data. To support non-destructive editing, the normal landscape height and material editing API was intercepted to allow redirection of edit requests to our own buffers and injection of the modified data back. This means the Unreal tools and the Unreal Landscape Renderer aren't working with the same underlying data anymore, but they are unaware of the change. By intercepting the landscape material pipeline, we allow for overlaying of material data by theme layers. By intercepting the landscape height pipeline, we allow for overlaying height data by the smart splines. We collapse together theme material layer contribution to form a material overlay and material mask. This is composited over the underlying Unreal material data to produce the resulting material layer passed to the engine. The height pipeline works in a similar way, except the overlay and mask come from rasterizing smart splines into a height buffer. In the future, we can overlay heights from themes for surface deviation effects, and we'll also compose themes from smart splines and objects too for richer spline-based objects. The same background processes that handle the mesh position calculations for the blocks are utilized to speed up the overlay calculation and recomposition in the editor. Moving a spline invalidates blocks. Each schedules re-render of spline height effects into overlays and recomposition in the background ready for a resubmit via injection to the actual engine height material maps. To achieve the visual quality bar we were aiming for with Legends, we undertook significant extension and modification of the Unreal graphics engine. The graphics engine team worked on many features for Fable Legends, a number of which are relevant to foliage rendering. Dynamic and instance lighting is particularly important for our dynamic foliage, but the graphics team also added features specifically to support it and to provide functionality it depended upon. We will look at these in a bit more detail. In Legends, we chose to use a fully dynamic direct lighting approach with our own light propagation volumes global illumination implementation, which we use to provide dynamic bounced light. This offers numerous workflow advantages in addition to the obvious visual fidelity improvements, such as accurate in-editor lighting, immediate feedback for lighting changes, full shadow emission support for the foliage we place dynamically. Our implementation was taken by Epic and is now offered as a general GI solution. We use screen-spaced ray-traced shadows as a method of increasing shadow detail beyond that available from our shadow mapping techniques. This approach proved robust enough that nearly all our small-scale instance geometry entirely relies on this method for their shadowing. This came as both a visual benefit, adding depth and richness to our scene, as well as a performance one, since rendering all this complex foliage into the shadow maps is very expensive. We can see the difference on the bushes here without shadows, and then with the shadows again. On the hedge here, without shadows, and with shadows. Ground cover is normally excluded from the LPV due to its high frequency and high cost, but there are some cases where this is desirable, such as these glowing mushrooms, which inject directly into the LPV to contribute a gentle area light to their surroundings. An artistic requirement for our foliage was for instances to be able to pick up their colour from the ground surface underneath. This makes the grass, our most common use case, match the ground closely, ties it down well, and introduces a bit of variation. This is performed on the GPU as a parallel projection render of the landscape into a temporary texture. A compute shader turns this into a vertex buffer with vertex colouring for the instancing shaders to use to apply it to each instance. This is performed at runtime only and with no offline colour storage required. To support arbitrary surface projection of foliage, we needed depth capture of the rendered meshes in the world. Use of collision meshes wasn't viable, as they tended to be of lower detail than the geometric mesh, and in many cases weren't even available. This capture is done automatically in the editor and saved out with the projector actor for use at runtime by exactly the same systems as the landscape foliage placement. By default, the mesh surface is captured at a resolution of 20 units, but can be increased if needed for a particularly detailed surface. A number of instance geometry culling optimizations and features were added by the graphics team. Visibility culling is performed per instance in a compute shader, and also allowed us to incorporate progressive distance culling and an optional scale-based fade. As a predominantly deferred renderer, we lack the ability to use opacity to fade out instances, so this gives a reasonable alternative to having instances appear and disappear in large blocks. The same system was also tasked with handling per instance level of detail, or LOD, selection, as the default per component handling wasn't sufficiently fine-grained, artificially boosting the LODs on lots of instances. An aesthetic requirement that later turned into a gameplay requirement was that all this lush foliage should interact with the action and movement of the players and creatures in the game. We already had some simple background wind effects using vertex shaders to add some movement, but we took this a step further with full obstruction detection and motion simulation. This meant all the foliage responds to player character presence. This effect is handled entirely on the GPU using compute shaders. An additional length we went to here was to generate unique pivot points for each strand in the foliage mesh, so that separate parts of each instance rotate around the point they intersect the ground, and not the common center point. This is almost completely automatic, based on adjacency information and thresholds, and meant a more detailed appearance can be driven cheaply from a simpler simulation. We have a fast GPU-based system for authoring and efficiently rendering individual highly detailed foliage assets. Using a shape definition mesh, density controls, natural variance, frond light attraction, and silhouette preservation, we can create lovely volumetric bushes and topiary. Now we've seen what's involved, we should look at the results, how well things worked out, what the benefits and considerations were. This isn't as clear-cut as expected, because there is more at play than just a size-speed trade-off. We may gain and lose in other areas, such as workflow, flexibility, scalability, iteration and control. We need to consider these across the various facets of the project. A significant premise for the original design was to save on offline data size and in-memory costs of traditional placed assets. This was because the source placement data would take up less space than the instance data based on it, a significant advantage of procedural generation. If we look at the dynamic generated data size and take this to be our placed content, we appear to end up with a bit more offline storage cost than we would like. But if you allow for compression and consider the extra burden scalability would put on traditional baked assets, then this may be mitigated. This is especially so since the benefits of the dynamic bake-free behaviour in Editor are very valuable. For now, the game as a whole is performing well, but we will investigate further ways to save space. Another premise was that in a world of ever-increasing load times, cycles were cheap and disk access our bottleneck. The theme system's dynamic placement from small source data was aimed at making better use of this resource imbalance. It turns out that the Xbox, having several cores, plentiful memory and pretty standard I/O, was a good match for this approach. CPU load was generally less of a problem with PC platforms. Here we see the background tasks working away alongside the rest of the game, independent of frame update, in batches of 5 or 6 at a time. Here, a series of theme system stats for a scene in-game with around 30,000 instances is in use. Tracking of blocks, including placement job setup, is consistently around a millisecond. Generation varies depending on load, but it doesn't affect the game thread as it's all in the background thread. Placement and removal again vary depending on load, around 2 and 0.2 milliseconds respectively. The first sample shows the system at rest with the player stationary. The remainder show maximum load as the player runs through the level. A number of the supporting features were moved to the GPU by our graphics team to offload work normally taken on by the CPU. On DirectX 12 we used async compute to run these compute jobs simultaneously with graphics work, allowing us to significantly reduce the cost and in many cases making it free. The instance counts are balanced to be in budget and with around 500 or 600 draw calls for most maps. Looking at the Unreal toolset, it was realised that we were going to need to accelerate all of the content creation steps in as many ways as we could. Building pretty levels can be time consuming, and the easier we could make the population, adjustment, balancing and refinement, the higher quality the results. Development of the technology and the tools to support it hasn't come cheap. I've been working on this at about a 70% rate over 3 years, with several of the graphics team spending time on the supporting features too. Since Lush detailed foliage was highlighted early as a key feature of the Fable Legends visual target, the cost of developing these systems has been considered a worthwhile investment, and it's certainly technology we could use on future projects. The end result of building these systems and applying these approaches is that the content creation process is very flexible and provides workflow and performance advantages over traditionally placed assets. Here are some of the other benefits. The dynamic nature of the foliage and lighting systems mean that our artists can quickly and accurately see the effects of their changes. This can be from simple parameter adjustment to painting a new brush to substituting whole themes. This ease allows more experimentation and refinement. Performance of the system can be balanced easily. Wide-reaching adjustments can be made via small data changes. The system is scalable. Densities and coverage ranges can be adjusted according to hardware capabilities. This system, along with others, scale down to the level of some onboard graphics chipsets, as well as allowing us to scale up and even add extra density and richness to high-end systems. Authoring is faster. Strokes of a theme brush affect many aspects of the ground surface and automatically adjust according to local landscape parameters. The techniques involved have allowed us to easily incorporate advanced features to get more out of the technology, for example, theme swatches for the villain view and non-destructive editing. We also provide some additional tools to help our content creators with their day-to-day work, for stitching adjacent landscape edges and cloning height data. These were added within our theme tool suite, as the tech we already had made access to the data simpler. Our art team have taken this system and really run with it. They've created some stunning scenery for our game to play out in. As they get ever more acquainted with what it can do, the results continue to impress. However, life is not always a bunch of roses, and nothing is without its issues, especially an ambitious piece of technology like this. There are things we should consider for future improvement, and perhaps reflect upon. There was concern over the fact that the placement of different meshes takes no regard for other meshes, resulting in a lot of overlap and intersection. This came partly from the graphics team, who were worried about the rendering waste from hidden geometry, and also from art, who sometimes needed to avoid unsightly intersection. At the moment, this has had to be addressed by the nature of the foliage, thin geometry where intersection isn't so relevant, and careful authoring and painting of themes. Procedural techniques, whilst deterministic, are subject to both chaotic variation and wholesale disruption. Whilst painting, the changing input parameters can result in wildly changing outcomes. This is an unavoidable annoyance, and an artist will typically paint until they're happy with what they see. Artists need to be aware, though, that this is susceptible to any algorithmic changes, be it fixing a bug, adding a feature, or improving efficiency. Another argument often cited against procedural techniques is the loss of control content creators feel. The computer is randomly placing things, seemingly never exactly where they want them. Whilst this is technically true, the bigger picture is that this level of automation allows them to focus on greater things. Sometimes artists can work around this with careful painting of a particularly dense theme, but there are still going to be cases where hand placement of assets is the tool needed to achieve the look thereafter. As mentioned, there is a trade-off between size and speed. We aim to take on the extra hit of CPU and GPU generation and computation over storing pre-computed instance, colour and lighting data. It may not always be the best use of the async compute of DirectX 12 and threading on multi-core machines for some games, engines or platforms. There is always a case for baking out the authored content and removing some of the runtime parts. More investigation is required, but the techniques employed here would still be valuable for content authoring even if only used at edit time. New and novel techniques usually come at a complexity cost, and there's no exception here. We decided to accept this cost of implementation and maintenance. We could have explored asset placement using automation using blueprints more, or waited to see what improvements came with successive engine versions. The latest version of Unreal now uses a few techniques similar to those described here, introducing a new procedural foliage generator, dynamic placement and better foliage tools, specifically to help build open-world games. Dynamic approaches can require other systems to also be dynamic. We had already decided to adopt a fully dynamic lighting system, but even if we hadn't, these techniques could still be applied, more obviously though with a baked approach to instancing meshes. Having developed this technology and tools, and as we are starting to learn how to play to its strengths, we are in a position to more efficiently produce content of the high quality expected from us by the Fable fans. Let's summarise by looking at what we've learned in getting to this point. After getting used to it, Unreal is proving a powerful framework within which to build custom tools to customise the rendering of and to enhance to meet your needs. It's not unexpected that good software takes time. It really is a case of you get out what you put in. By planning ahead, taking our time on the design and architecture, and maintaining high quality standards, we have reaped the rewards. Much of the later development has been made considerably easier thanks to earlier planning and design we undertook. For a lot of the systems involved, it was far more important that they were correct and understandable before they were fast, especially when the techniques needed to be developed and refined. We have revisited many of them at a later date to rewrite and optimise, but mostly only as indicated by profiling and when the scale of the game started hitting limits. Many of these cases were expected, but equally there are comments anticipating a need for speed still in the code to this day. The naive placement algorithm was never meant to be used in production, but has proved surprisingly effective. The first implementation was used over 2 years ago. I had planned out and was expecting to need a much more complicated and powerful system. The power to easily flood a level with geometry made us take great care over the exact construction and setup of each mesh used. The need for high densities made low poly models and good levels of detail important to investigate and optimise. Another aspect of their creation relating to the placement and general surface filling requirements of the meshes is that round footprints work well. There are ways to trade size and speed at many levels and in many places in software engineering. These techniques have provided us with another fairly high-level way to do this. By using procedural techniques and automated processes, we shift content creators away from lower level and more laborious tasks to places where they can really apply themselves creatively and be more productive. They are choosing elements to tweak to improve a few theme assets rather than spending hours manually redressing acres of grassland. Whilst all you have seen can be done with the base toolset, improved tools are the only way to amplify a person's effort. They are a lever, allowing people to get more done, to apply themselves more efficiently. Powerful tools help us improve workflow, quantity, and quality. As a tools programmer, my job is to empower people, to amplify their talents. Tools with the power the theme system brings are a great way to do this. A world in a brushstroke, if you will. Thank you for listening.